right, thank you all for joining. I think we will get going now. So my name is Colin Murphy. I'm the Deputy Director here at the UC Davis Policy Institute. Appreciate you all for taking the time to join this webinar, where we will be discussing the results of a recent research project evaluating the air quality impacts of Oregon's proposed clean fuel program changes. Miriam, apparently I wasn't given screen sharing privileges, so can you please, yeah, I think I need to be a host for that, not a panelist. Apologize for the technical glitches here. There we go.
I'll try it now.
Perfect. Okay, can you see my screen? Yeah, great. Okay, so thank you all for joining. Before I go any further, I want to recognize the research team as well as the people from ITS, including Miriam McDonald, who has been helping us deal with the technical glitches this morning, Sarah Schramer, the program manager and communications director for the Policy Institute, as well as Corianne Wind and her team at DEQ and the rest of the Oregon staff. This project could not have happened without everyone's contributions. I especially want to recognize the research team, including Mike Kleeman, who you'll hear from in a few moments. He's a professor of civil and environmental engineering, and he led the air quality and health impact modeling effort. Also, possibly on the webinar, but not planning to speak today, are Guihua Wang, who's a research engineer here at ITS Davis, who led the MOVES modeling, and Yiting Li, PhD candidate in Mike's lab, who played a major role in getting the air quality modeling moving forward. So this project actually started about 3 years ago with an email from Corianne Wind to me asking if there was a quick and simple way to estimate some of the air quality benefits of the Clean Fuels program. And at the time I thought, sure, that's not a big deal, a couple hours of work to put some numbers together and get a back of the envelope estimate. 2 months later, I sent her an email saying, no, it's not a quick and simple thing, but we could do a really cool research project to actually do this for real. And lo and behold, it became this. So we're going to go through a little bit of background on the Clean Fuels program and some of the work that's going on. We'll talk about the vehicle emissions modeling, and then Mike will take over and discuss the air quality modeling and health impact analysis. And then we will conclude with what it means for the Oregon Clean Fuels program expansion. Now, I know from looking at the attendees, a lot of you are folks who have been attending the rulemaking advisory committee meetings and other rulemaking engagement opportunities around the Clean Fuels program in Oregon. So for many of you, this background is going to seem fairly familiar, but because we're going out to a somewhat wider audience today, I wanted to give people a little bit of context for how this rulemaking and this program came about, so the lay of the land is clear. So first, I think for those of you who aren't terribly familiar with clean fuel standards and fuel policy, there's a question of sort of what is it and why does that happen? And first of all, I'd say that here at the Policy Institute at UC Davis, we are happy to go into depth and spend a lot of time talking about these policies and what they do and how they fit into the portfolio of climate policy. That's not what we're talking about today, so we're going to sort of abbreviate this to one slide. And really the question is, why do clean fuel standards like Oregon's Clean Fuels program matter? And it's because transportation is a really difficult sector to reduce emissions from. The rates of change are extremely slow because vehicles last a long time. So the fleet, a vehicle, once it's sold, might be in the fleet for 15 to 20 years, possibly even longer. And that means it takes a long time for the fleet to turn over. And while reducing the amount of motorized travel can be an important element of sustainability policy, urban land use design is also not quick to change. So one of the things that we've come to realize in the transportation studies space is that it's difficult to meet meaningful greenhouse gas reduction targets with kind of an EV only approach, even though we know that EVs or electric vehicles, particularly battery electric vehicles, are probably the single most important technology for meeting our long-run climate goals and essential for success. We went through a really deep modeling exercise in California, which produced a report driving California's transportation emissions to zero. I led the fuels section on that, and this really talks about how California could get to a net carbon neutral transportation system by 2045. And one of the things we learned is no matter how hard we pushed EVs into the system, an EV-only approach could not meet the critical climate goals necessary to avert the worst impacts of climate change. So you need to be able to reduce emissions from these existing fleet of vehicles. That means you need liquid fuels, and biofuels present an opportunity to reduce emissions there, but you have to have a life cycle analysis based policy in order to avoid getting fuels that are not really beneficial. So a life cycle based fuels policy is pretty much the short description of Oregon's Clean Fuel Program or California's Low Carbon Fuel Standard, which are very similar. So borrowing a couple of slides from Oregon here. Oregon has adopted a broad and comprehensive portfolio of greenhouse gas reduction measures, including things focusing on the stationary sector, the electrical sector, and several transportation sector policies, of which the Clean Fuels Program is one of them. And as somebody who spends a lot of time thinking about, researching, and talking about climate policies, this sort of broad portfolio is the right way to go, and a Clean Fuels Program is really an important component of that portfolio. In 2020, there was an executive order issued that specifically called out the Clean Fuels Program as one of the key tools the state needed to meet its long-run targets. And it specified at least a 20% target in the program by 2030 and 25% by 2035, as well as some other targets and goals for the program. So as a result of this, as well as Oregon's just ongoing commitment to strong climate policy, there's been a process to begin adopting new rules and amending the program to help it make sure that it can meet the challenges of decades to come. So as part of that process, the Department of Environmental Quality contracted with ICF, which is a consultant that does a lot of work in this space, to model changes to Oregon's vehicle fleet from likely policies, including the Clean Fuels Program, and to develop some compliance scenarios, basically a description of how Oregon could meet these new targets, given realistic conditions. They also contracted with us to model the air quality impacts of these changes. So we ended up modeling 2 of the proposed compliance scenarios plus a business as usual case to compare it from. And DEQ has held several workshops over the last several months to discuss elements of this proposed program and seek input. So the link to the DEQ rulemaking page is right here. We are not part of DEQ, and this workshop is really meant to be focused just on the air quality modeling and the air quality impacts. General sort of program or regulatory design questions should be addressed to DEQ, or feel free to reach out to me. This is something that we're engaged in and I personally love talking about, but we want to focus on the task at hand today. So with that, there are a couple of different scenarios modeled in this study. So sorry, I was checking the chat to make sure. The business as usual scenario, really we had to have something to compare against to see what the effects of the compliance scenarios would be. Under this, you have no real policy activity beyond the baseline year. And this means that there is a very small Clean Fuels Program effect baked into the baseline. In 2017, the Clean Fuels Program had a 0.5% carbon intensity reduction target. So it's not a perfectly clean baseline, but 0.5% is a very low target. The amount of impact it was having on the vehicle and fuel pool is relatively low then. So we're confident that influence is not biasing the results of the modeling we did here. The 2 compliance scenarios are called Scenario A and Scenario C, so they match their names in the ICF report where they were generated. The first scenario, Scenario A, looks at a 25% Clean Fuels Program target and then models the impacts of things like the Advanced Clean Cars 2 and the Advanced Clean Trucks program, which are largely focused on supporting zero-emission vehicle, mostly battery electric vehicle deployment in Oregon. And the effect of these programs was enough to provide enough Clean Fuels Program credit to meet the 25% target in 2035 without requiring a lot of other changes elsewhere in the vehicle or fuel pool. Because we're looking at air quality, we did have to consider the effect of non-transportation sources. So that's industry, home heating, every other activity, both natural and man-made, that would impact air quality. We assume no significant changes in the net emissions. Obviously, over the next 15 years, there are going to be some sources of emissions that emerge and some that decline. But because what we're really interested in is the impact of the transportation changes, making the same assumption across all scenarios for non-transportation emissions lets us isolate what the effect that we're particularly interested in. Scenario C reflects sort of a higher clean fuels program target. Ultimately, it was set at a 37% target that was judged to be sort of the best blend of ambition and realism to make sure that there was, you weren't pushing farther than the fuel providers and vehicle providers could go. And so really what this was is, in addition to scenario A, there were some additional liquid and gaseous fuels that entered the Oregon market. The biggest change is 25% of the liquid diesel pool in 2035 was displaced by renewable diesel, which has a lower carbon intensity and some very small benefits for air quality. There are also some other gaseous fuels, particularly a little bit of renewable natural gas. Again, no significant changes. And so really this was meant to look at how far the state could go beyond that 25% target by adopting additional measures. Now, that 25% displacement of diesel is pretty much where California is right now. We've had a low carbon fuel standard for longer than Oregon, and currently about 25% of our diesel pool is made up of renewable diesel, so that was judged to be a very reasonable and realistic target. So with that, I'm going to move on to the vehicle modeling, and I definitely encourage everybody to be dropping questions into the Q&A section. We can have, if there are simple questions, the other panelists can answer them while we're talking, and otherwise we can save them for Q&A at the end. We have reserved hopefully at least an hour for discussion and Q&A on this, so I certainly encourage you to take advantage of that. So the first phase of this research project was modeling the emissions from the new fleet of vehicles and fuels in Oregon in order to figure out sort of what's coming out of the tailpipe. And then we worked on what happened to the pollutants after they came out of the tailpipe. The main tool we used for this is the EPA Motor Vehicle Emission Simulator, or MOVES model. And MOVES takes the vehicle fleet and fuel portfolios and vehicle activity levels and can simulate the activity and generate county level emissions for that vehicle fleet. And the model has default data and default projections out to certainly far enough in the future to work for the study. But the problem is that the default values included in the model do not really reflect what we currently think are the likely changes to vehicle portfolios, and this certainly includes Oregon. So the first major task was to update the MOVES model to have a more realistic projection of the changes in vehicles and fuel. So we worked with the Department of Environmental Quality, the Oregon Department of Transportation, ICF, and others to get a more realistic and likely trajectory for the developments in the Oregon vehicle and fuel pool, and then reran the MOVES model for every county in Oregon. And this was actually a very computationally intensive operation. It took many days, often over a week of just computer crunching time to get the results out. Those results were reviewed by Oregon staff for quality assurance. And once we were satisfied that everything was working properly, those were the county level emissions. We have provided those county level emissions to Oregon as part of this project, and those can be used as the basis for future research. And in fact, that's currently ongoing right now. So I wanted to show a couple of the kind of aggregated state level results of this updated MOVES modeling. So what we see is 2017 is sort of the current year, which is largely based on data and very near-term projections. The middle column is the projections from the default. So what we would have been modeling had we not done this step to update the MOVES vehicle and fuel assumptions. And then 2035 is the right-hand column, the 2035 MOVES BAU represents the vehicle fleet after we did the adjustments. And we're looking at VMT here, which is vehicle miles traveled, and that's an assessment of vehicle activity, and there's obviously a very strong correlation between VMT and pollution. So what we see is the MOVES defaults would tend to underestimate the amount of heavy duty vehicle activity, trucks and buses, and overestimate the amount of light duty vehicle activity. And obviously, given that we are concerned about air quality, getting those more accurate is of prime importance. So that's really what we did with that moves modeling step. Here are the pollutant emissions, both for the BAU as well as scenario A and C, all in kilograms per day. Again, this is aggregated at the statewide level. So this sort of tells us, gets us into the ballpark of what the health impacts are going to be. But really, we just looked at it to get a sense of statewide trends as well as for quality assurance. And again, what you see, both scenario A and C, there are significant reductions across basically every pollutant that is of interest, and that's going to be modeled later in this study. So with that, we're getting to the air quality modeling and health impact analysis. So I'm going to turn this over to Dr. Kleeman. I'll keep running the slides, just tell me when you want to advance. And Mike, go ahead and take away from here.
Thanks, Colin, and hello, everyone. So my role in the project was to do the air quality analysis and the health impacts analysis resulting from the adoption of the cleaner fuels. And we, of course, want to do this at higher resolution than statewide. We want to be able to get to a more localized effects because we know that the traffic pollution is very localized. It's concentrated around the transportation corridors in our cities. And so we need something better than statewide, and we need something better even than county level. So we wanted to try to host this in a realistic framework. And so we have to have the emissions from all the different sectors, not just the transportation sector, in order to start the analysis. And we built those using the National Emissions Inventory provided by the US EPA, processed using the smoke emissions processor. And then we did several scenarios that Colin described in the future, but we also wanted to run a scenario in the present day to make sure that our system was capturing reality before we projected out into the future. So we'll talk in a little while about those results for a present day simulation in 2016, actually, before moving on to the 2035 scenarios. Now, downscaling the emissions to the local level, 4-kilometer resolution is what we were aiming for, is a little bit tricky. And we've done this sort of exercise in California before. And so we adopted the same methods that we used in California in Oregon for the analysis. And basically what we do is we take those county level emissions from the MOVES model, and we will develop a scaling factor between the present day emissions and the future in that county. And then we will use the smoke generated 4-kilometer emissions inventory for current conditions. And we will scale every grid cell in that county by that scaling factor that we get from the MOVES model. So this gets around the need to do any sort of complex travel demand modeling and sort of network type analysis for the transportation system in the future. It gives us an efficient way of trying to estimate what the changes will be at the 4-kilometer resolution level without going through all that complexity. So that's the approach that we adopted here. And again, we've used that in California previously. The other sectors, as Colin mentioned, were not changed. So the point sources and the area sources that are in that national emissions inventory were kept static. And the assumption there is that we will not be having any major changes that would distort the effects of the transportation emissions that we're going to be focusing on. So the idea is here that we're going to try to look at the clean fuels effects without getting too worried about second and third order effects about the refining of the fuels and the other things that would potentially happen, that could affect emissions in other sectors. So all of that complexity certainly could be adopted in the future, but this was our first cut analysis at the problem. And so we did not include that level of complexity in this. Wildfires are a big thing now in both present day and probably in the future. We included wildfires in our present day analysis as we're trying to validate the modeling system, but we did not use wildfires in the future, again, for that same reason. They're not directly related to the transportation emissions. And so we're going to be focusing on transportation. So we left wildfires out of the future. We do have the natural emissions from the vegetation though. So in addition to all the the man-made emissions, we have the natural emissions from plants, and that's handled with the Megan model. So Colin, next slide. This is just a quick picture of the emissions at that 4-kilometer resolution across the major transportation corridor in Oregon, the I-5 corridor running through many of the major cities. And looking at the on-road gasoline emissions on the left, and then the on-road diesel emissions on the right, and both of them following that I-5 corridor, and both of them having hot spots over the city. So this spatial pattern is going to be preserved in the future. What we're going to be doing, though, is sort of adjusting these emissions up and down based on what the MOVES model tells us county by county to account for the effects of the low carbon fuel adoption. So this is really just to get an idea of spatially. If you're interested, these units on these plots, I think, are micrograms per meter squared per minute, kind of an esoteric unit, but that's the sort of modeling thing that we would need to keep track of as we go forward. All right, so let's go to the next slide. So Colin already touched on this a little bit, but it bears repeating, I guess. Just looking at the total emissions changes and trying to get a little bit of perspective about the changes that we can see in the inventory before we go to the trouble of trying to analyze it with the chemical transport models that we'll talk about in a moment. So if we look at the different scenarios across the rows of this column, we've got the 2017 base case, and then we've got the 2035 business as usual case, and then the 2 scenarios where we adopt the low carbon fuels. And each of the columns shows then a pollutant. We've got the NOx, the PM 2.5, the SOx, and the ammonia, all things that are criteria pollutants that will affect the air pollution. Now, what we see is that there's not a major change in statewide total emissions due to the adoption of the fuels. You can see that there's definitely an effect, but it's not as if we're going to cut the statewide PM 2.5 emissions in half by the adoption of these fuels. So I think it's just important to start with these perspectives, and that stems largely because, again, the transportation emissions don't necessarily dominate for some of these criteria pollutants across the statewide. There's definitely an effect. We can see that the on-road gasoline emissions, we reduce 25% for PM. If we just look at the PM emissions from the on-road gasoline vehicles due to the adoption of the low carbon fuels, and we had reduced 22% for NOx, but again, in the context of those statewide totals, it's not necessarily dominant. And here's where then it matters, where it happens. And, we need to analyze the situation around the cities and trying to understand then on a fine spatial grid, what can we affect these changes to sort of cause in the air quality in the system. So next slide, please. So we wanted, again, to try to make sure that our modeling system was capturing reality when we projected out in the future. And there's, in addition to the emissions inputs that go into these reactive chemical transport models, we also have to input the meteorology, the wind speed, the wind direction, the temperature, the humidity, all of these things. And it's a little bit challenging in the future scenarios because we don't have the benefit of historical observations. In historical episodes, when we run the meteorological model, we can use the measured wind speed and wind direction, the measured temperature, to sort of anchor the model to reality. But when we do that in the future, we don't have that luxury. And so when we did our present day analysis, trying to build confidence in the modeling system, we also didn't allow ourselves that luxury in present day either. And so these weather predictions, essentially, that we're using to drive the chemical reaction transport model, these weather predictions were all done without the benefit of any sort of data analysis forcing in the model solution. We still do pretty well, but we notice that we have periods where the wind speed, let's say, as a function of the time of year on the lower axis, the wind speed on the vertical axis in the upper right panel, that is being over predicted, the blue line compared to the orange line. And that's going to cause dilution, and that's going to cause an under prediction of concentrations then when we do the air quality analysis later on. That's all for January in the upper right panel. In the lower right panel for July, those under predictions are muted a little bit. So we know that some of that bias is sort of present in the winter, but not as present in the summertime. And so we wanted to know those things about our modeling system because we're going to have to live with them in the future as well. The other thing that we think that we learned in this process was that maybe we didn't understand some of the wood smoke emissions as well as we hoped we would from the national emissions inventory. And so that'll come out again, I think, as we go through the comparison between the present day simulations and the present day values, trying to build confidence in the modeling system. So next slide, please, Colin. So our overall system then is going to use a research chemical transport model that's somewhat similar to CMAQ, but it has certain advantages that we've built into it over time. And one of the main ones that we'll be using in this process is the source tagging feature. So source tagging is a way to try at the emission stage to attach a tag onto the criteria pollutant emissions that are released from different sources. And I've listed 9 of them here, including 2 of specific interest, the on-road gasoline vehicles and the on-road diesel vehicles. And we can follow that tag then through all the calculations that happen in the chemical transport model. So we can follow it through the emissions, the transport, the deposition, and all the chemical reactions that are happening, and trying to understand then at the receptor sites, all the grid cells across the whole modeling domain, how much of that pollution came from each one of these 9 different sources. And that's a feature that we use a lot in our model, and we'll use it in this project as well. We also have more size resolution in our model. So we have 15 or 16 different size bins, and we look at things like ultrafine particles and other research grade questions, in addition to sort of the regulatory PM 2.5 questions that CMAQ can handle. So that's why we're using this model in the project. So what we're going to do then is try to apply it and look at the predicted outcome of the different emission scenarios, trying to understand then what's the exposure field or the concentration field across the entire state at 4-kilometer resolution, trying to build up a long-term average. Now, we'll talk a little bit about how we build up that long-term average in a second, but I want to try to focus on sort of more confidence building in the modeling system. So next slide, please, Colin. So these are the simulations that we did for the present day atmosphere in Oregon. We chose a 2016 time period. We were familiar with that year. And we are looking at then annual average predictions. So we modeled the whole year, all 365 days. And we're looking at different features of the PM 2.5 that is predicted by the modeling system. In the leftmost panel, we have the total mass, and that ranges up to 8 micrograms per cubic meter in the urban areas. And then in the second from the left panel, we have PM 2.5 elemental carbon. Elemental carbon, that black city carbon, is a component of PM 2.5 mass. And it's emitted from transportation sources. We think it has health effects. You can see fairly sharp spatial gradients around the urban areas for that PM 2.5 component of the total mass. The third from the left panel then shows the concentrations of organic compounds. These are anything that is containing carbon, hydrogen, oxygen, other things in an organic molecule. It is emitted from many different sources, not just transportation sources. Biomass combustion, wood burning, food cooking, other sources all release organic compounds. And so you see a broader spatial distribution, but perhaps still somewhat focused on the urban areas. And then on the rightmost panel, we see PM 2.5 nitrate. So nitrate is an inorganic salt. It's formed largely in the atmosphere from gas phase precursor emissions of oxides of nitrogen, NOx, which we're emitting from our mobile sources. After that is reacted to nitric acid, it can combine with ammonia and then form ammonium nitrate salt, which condenses into the particle phase. And that's what we're looking at here. And you can see that that's a much broader spatial distribution, not necessarily focused on the urban centers. And that reflects, again, that secondary production process. So these modeling systems are trying to produce concentration fields from both the primary emissions, it was emitted as a particle, spent its whole life as a particle, and things that are secondary, means it was emitted as a gas, and then it reacted and formed a particle in the atmosphere. And we're trying to capture both of those things in the system. So you can get an idea then. We generally have a background of sea salt blowing in off the ocean. You can see that sort of yellow on the leftmost diagram. That largely falls out of the atmosphere before it reaches Oregon's urban centers. And then we have these urban islands that are largely driven by the emissions in the cities. And you can get an idea then for the different spatial sort of distributions that can result for the different components that are coming out of this. So Colin, next slide. We also have PM 0.1 mass. That's got even sharper spatial gradients. And you can see just to the east of Eugene, a point source emissions from that. And then if you look a little bit north of Portland, another point source emissions. That one north of Portland, I know, is driven by the airport. And so the sources that dominate ultrafine particles, PM 0.1, tend to be different than the sources that dominate the PM 2.5 particles. And so you kind of get a different spatial distribution. Again, PM 0.1 was a little bit of an exploratory research topic within the framework of this larger project. And so we won't focus on those results today, but just want to point them out as we go along. So Colin, next slide. All right, so that tagging feature allows us to look at the mobile source contributions to the PM 2.5. And so here I'm not basing this on a chemical component like elemental carbon or organic compounds. I'm looking at all the primary PM that was emitted from the tailpipes of on-road gasoline vehicles in the left diagram. And I'm looking at all of the primary particles that were emitted from tailpipes of diesel vehicles on the right diagram. So the concentration distribution, it has a similar sort of spatial distribution. You can see again the transportation corridor connecting all the major cities, I-5, and then the focus around the cities due to all the different vehicle miles traveled in those locations. The magnitude is different though. We've got around 0.35 micrograms per cubic meter in the gasoline vehicle tailpipe contributions. And then we've got around 0.8 micrograms per cubic meter peak from the diesel vehicle contributions in the year 2016 annual average. So we're using all of that information later in the project to understand the health effects of changing the fuels and changing the emissions from these different sources and how that will play out. Now, what's not shown on this, though, is the tire and brake wear, which is another component of the transportation contribution to PM 2.5. And we'll sort of discuss that a little bit more deeply later on. So go ahead, Colin. So here we're showing a comparison between the predicted concentrations and the measured concentrations at 4 sites around the modeling system where we have high populations. So 2 sites in Portland and 2 sites in Eugene. Each of these time series then has the day of year on the lower axis of them, and then the concentration of PM 2.5 mass on the vertical axis. The dots are the measurements, and the lines are the model predictions. So what we can see is that the modeling system does a pretty good job in the middle of the year capturing the concentrations of the PM 2.5 in all of the observation sites that we're looking at here. But perhaps in the colder months, in the early part of the year and the later part of the year, we have some under predictions of that. That gets back to that wind speed over prediction that I talked about. And then it also gets to the wood smoke emissions from fireplaces, which perhaps are under predicted in the National Emissions Inventory. So we think that this result will not overly bias the analysis of the transportation sources, because again, it's driven mostly probably by that, that fireplace sort of issue, and are we capturing that correctly? It's not to say that the vehicle emissions are inaccurate. If the vehicle emissions were inaccurate, our predictions in the middle of the year would be off, and they're not. So it's some sort of a seasonal effect, and we think that we're satisfied with the performance in the modeling system. We pass some of the criteria that we usually hold ourselves to whether or not this modeling system is working correctly at this location. And so We go into it with our eyes open, again, because we have to configure the models in a way that we can't use the present day meteorology to sort of force the wind speed and wind direction. And because we have to live with some of the issues in the emissions inventory, we're going into it with our eyes open, but we think that the system is working well enough to get information out of in our future scenarios. So next slide, please. So in the future scenarios, we're interested in building up a long-term average, basically an annual average is what we'd like, but we want that annual average to be representative. We have, the effects of the El Nino Southern Oscillation in the West Coast of the United States, which means that depending on the year, you can have a very wet year or a very dry year or anything in between. And that affects air quality as well. It matters if we're getting a lot of, weather systems blowing through, a lot of rainstorms. It changes things, we need to have a longer term analysis in order to smooth all of that out. One approach for doing that would be just to model 10 years and to try to use that long-term average to estimate a representative annual average concentration. But that's really computationally expensive. This is already a supercomputing exercise, and to do 10-year analysis then turns it even more of a supercomputing exercise. And so the approach that we've adopted based on our work in California has been to select a random sample across that 10-year window and use the information from that random sample to estimate what the long-term average is. So that's like anytime you go out and you want to know the average weight of the people in California, you don't have to ask them all their weight. You can select a random sample and get the weights of that random sample, and then you can get a pretty good estimate of what the population weight is. So we're doing that same thing here, trying to avoid the computational burden of doing every day of the 10-year window. Now, just like in the example of trying to do a sample and estimate weight, the bigger the sample size, the more accurate your estimate will be. And so we did some work trying to figure out how does our estimate improve if we have more and more sort of days in that sort of representative sample across the 10-year window. And what we came up with was that 32 weeks randomly spaced across the 10-year window is enough to give us a pretty accurate estimate of the long-term concentrations to within, say, a fraction of a microgram per cubic meter, and perhaps even more accurate than that for the population-weighted concentrations that would be developed through that method. And so that's the approach that we adopted here, was to randomly select 32 weeks between the year 2030 and 2039. And we're going to use that to develop a 2035 estimate. The emissions inventory will be sort of static for that whole thing. It's just the meteorology that's changing. It's our way of trying to deal with ENSO cycles in the presence of trying to understand what's going to happen in the future. Okay, so next slide, please, Colin. So here then is an estimate of the annual average concentrations in 2035 in the business as usual, the scenario A, and the scenario C, or I'm sorry, the difference between the business as usual and scenario A, and the difference in the business as usual, I'm sorry, scenario A and scenario C. So I'll walk through each of these trying to explain them. The 2035 plot on the left is sort of comparable to the 2017 plot that I had earlier in the presentation. It's the annual average concentrations, and we're looking at, again, some hot spots that are developing around the urban centers, but not as hot anymore. You can see that we still can pick out the transportation corridor, but we don't have the same amount of sort of concentration gradient around the urban centers. And that's largely reflecting then the changes to the emissions. So we've got the scenario A minus the BAU in the middle slide, where we're looking at how much that PM 2.5 reduces compared to the business as usual scenario due to the adoption of the low carbon fuels. And you can see then these effects are pretty isolated over the transportation corridors. And you can see something on the order of a 0.15 microgram per cubic meter reduction in the PM 2.5 mass coming out of that adoption of the low carbon fuels. And then moving from that scenario A to scenario C, how much additional benefit would we get in the reduction of PM 2.5 mass? You can see that here they're a little bit more modest. We've switched units now. Instead of micrograms per cubic meter, we've got nanograms per cubic meter. And we're getting something on the order of an additional 20 nanograms per cubic meter due to the adoption of those broader adoption of the low carbon fuels. Remember that those were largely occurring in diesel engines. By the year 2035, most of the diesel engines already have an emissions control device like a diesel particulate filter installed on them. And so even though we have a good greenhouse gas benefit from the adoption of those low carbon fuels in the diesel engines, the tailpipe emissions were already really controlled in those scenarios. And so we don't get a lot of additional benefit for particulate air pollution due to the adoption of, further adoption of biodiesel in those scenarios. So next slide, please, Colin. We can also look at the distribution of the different components that we discussed earlier. So remember, elemental carbon was that black carbon component of the PM 2.5 mass. The layout of these figures is identical to the one that we just went over. So the leftmost panel shows the business as usual prediction for that concentration in 2035. The center and the right panels are difference plots. They look first at the reductions due to the adoption of scenario A, and then the further reductions due to the adoption of scenario C in the concentration fields. So we can see that the business as usual concentrations for elemental carbon had a peak at around 0.3 micrograms per cubic meter in the urban areas along the transportation corridors. And when we adopt the low carbon fuels, again, I've changed units. I've gone from micrograms to nanograms. We get a reduction of around 20 to 30 nanograms per cubic meter in that black carbon, that elemental carbon concentration field. And then if we go to the scenario C, we get a further reduction of around 3 nanograms per cubic meter. Again, all of the scenario C sort of enhancements are going to be somewhat modest because of the already stringent emissions controls on those diesel engines in the future. So next slide, please, Colin. This is a similar picture for the organic compounds that are part of the PM 2.5 mass. So again, the business as usual concentration field on the left, we've got concentrations approaching 0.8 micrograms per cubic meter. And then when we adopt the low carbon fuels in scenario A, we get a reduction of around 40 nanograms per cubic meter. And then moving into scenario C, we get a further reduction of around 3 nanograms per cubic meter due to the adoption of the low carbon fuel. So again, somewhat modest, but all focused on the urban areas where it will have a health effect. And then next slide, please, Colin. These are the pictures for the gasoline tracers then. So this is the total amount of tailpipe that is associated with gasoline vehicles in the atmosphere now. These are concentrations, not emissions. So this has been tagged and followed through the atmospheric simulation. So the leftmost figure shows the business as usual concentrations, and that has values of around 0.25 micrograms per cubic meter. And then looking at the reductions in scenario A, we get a reduction of around 40 to 50 nanograms per cubic meter of that mass of primary particles emitted from the tailpipes of gasoline vehicles. And then a further reduction in scenario C of around 2 nanograms per cubic meter. And then next slide, please, Colin. And this will be the same thing for the on-road diesel tracer. So we've got around 0.3 micrograms per cubic meter in the business as usual scenario, and then that's reduced by around 30 to 35 nanograms per cubic meter in scenario A, and an additional 5 nanograms per cubic meter in scenario C, sort of getting progressively additional biofuels into the fleet. All right, so next slide, please, Colin. So in summary then, there's changes that are apparent along the transportation corridors and in the major cities including Portland, Salem, and Eugene. And it's largely following the expected trends. We see reductions in the components that we know are associated with on-road vehicles. So that's elemental carbon, and then the tracers for the gasoline and the diesel vehicles all decrease by more than the PM 2.5 total mass, because PM 2.5 total mass has big contributions from non-transportation sources that we held static in this analysis. So we got our biggest reductions between the business as usual and scenario A, and then we had more modest reductions between scenario A and scenario C in terms of the criteria pollutant emissions and the particulate matter concentrations in the future. So next slide, please, Colin. So we wanted to know then what the health effects would be from these changes in the airborne particles. We focus on airborne particles because that's the majority of the public health benefit. When we do the analysis, ozone certainly has an effect, but it has maybe 10% of the effect that the airborne particles do. And so this first cut analysis, we really focused on PM 2.5 and changes to PM 2.5 to estimate the health benefits due to the adoption of the low carbon fuels. The tool that we're using for this is the BendMap model that's maintained by the US EPA. And we used a combined distribution of our exposures from our model simulations with the present day population that we obtained from the 2010 census. We use health impact functions. There are many that are available in BendMap. We chose the Krusky et al. 2009 health impact function, which is a pretty standard one for estimating the health benefits of reduced air pollution. And then we are finally going to try to put a value onto the public health benefits with a term called the value of a statistical life. And so if you're not familiar with this, the idea is that we can estimate people's tolerance for risk. And we do that by looking at the differential pay scales for different occupations and compare that to the dangers that are in different occupations. And so, being an office worker in California has a very different risk profile than being a salmon fisher in Alaska, and those things pay differently as well. And so it's through that comparison that economists have come up with this idea of a value of a statistical life. What's your, what dollar sign do you put on to air pollution? Because it increases your risk of dying. And how do you estimate that in monetary terms? And this is what it turns out into, around $7.6 million in present day terms per life of public health benefit for every avoided mortality. Now, to do the BendMap analysis, BendMap is always comparing two things. And so we have to use that in our analysis as well. So when we do the present day analysis of health effects in Oregon, so this was our 2016, 2017 simulations, we're going to have a comparison case that assumes a clean 3 micrograms per cubic meter of PM 2.5. So if no one lived in Oregon, that was the assumption. You'd have 3 micrograms per cubic meter. And we'd have no gasoline or diesel vehicles. And so we assume 0 micrograms per cubic meter for those calculations. In all of our future analysis, we're going to be comparing everything to the business as usual case. So we will compare scenario A to the business as usual case, and then scenario C also to the business as usual case in order to develop an estimate for the health benefits associated with those scenarios where we adopt the low carbon fuels. Okay, so next slide, please. And we'll talk just really quickly about mortality is the the metric that I'll look at today. Deaths, excess deaths due to air pollution, but that really just underlies a whole range of health effects that tend to get broader as you go to lower severity events. And so a few people die, but more people end up in the emergency departments because of asthma or other health ailments, and even more are at the doctor's office or have absences from schools or from jobs. And even more than that, have respiratory symptoms, maybe wheezing or other type of things. And, sort of as you go down in severity, you get much broader affected. So even though I'm going to talk about, deaths in the next slide, you really have to keep in context that this is just one metric of a much broader health effect that we're really trying to get a feeling for here. So next slide, please. So here are the results from the BendMap analysis. And this is a complicated slide. And so we're going to spend some time going through this to try to understand it fully. So I want to start looking at just the PM 2.5 section of the table. And so we'll focus on those first 3 rows of the table. And we've got 3 rows associated then with the business as usual scenario, and then the savings that we have in scenario A, and then the savings that we have in scenario C. Now, what we're showing here is the mortality, the total mortality, or the mortality per million people in the analysis. And BendMap works by looking at mortality, and the assumption there is that only people older than 30 would be subject to, a risk of death due to air pollution exposure. That's the Krusky function. And so that's what we'll be focusing on here. So the business as usual scenario then has around 242 excess deaths per million people in using the exposure fields that we developed for 2035. And we estimate then that under scenario A, we would avoid around 5 of those excess deaths due to the adoption of the low carbon fuels. In scenario C, that estimate goes up slightly to, but it's still around 5 excess deaths avoided per year due to the adoption of those low carbon fuels. But again, remember that underlies a whole range of other health effects. This is just sort of the tip of the iceberg when we talk about the health effects. Now, the economic value of that then, those 242 deaths per million people, or if you look at the total mortality across the entire state, then that's a big number. That's, on the order of, $4 billion. And then if we wanted to estimate the savings that are associated with the adoption of low carbon fuels, that's, then on the order of $84 million per year that would be avoided. Again, not just the mortality, but that underlies this whole other range of health effects, avoided doctor's visits and all these other things that impact our system. Now we can look at where that's coming from in the other sections of this table by, using the tagging information in the model calculations and trying to estimate, is it mostly coming from diesel? Is it mostly coming from gasoline? And what we see is somewhat equal effects, to the first order approximation from the gasoline and diesel contributions to that excess mortality from the primary tailpipe emissions. And that only accounts for a fraction of the total. Some of it's also coming from the reduction in the secondary nitrate, which is not reflected in any of those lower sections of the table, but it is reflected in the total PM 2.5 mass contribution part in the upper part of the table. So overall, we get a contribution from the tailpipe emissions from both primary emissions from both gasoline and diesel vehicles, and their NOx emissions, which would be converted to nitrate. That all matters in this analysis. And that sort of speaks to some of the complexity that you have to have in these chemical transport model calculations if you want to really understand what's driving the cause-effect relationships between the low carbon fuels and the final health benefits that we're seeing. So next slide, please. So the final thing that I want to talk about is more just returning a little bit to that research impact, looking not just at PM 2.5 mass, but looking at ultrafine particles, PM 0.1 mass. So these are emerging pollutants that we don't fully understand their public health consequences yet. We know that they get everywhere in your body, and we know that toxicologists, people who do animal exposure studies or cell exposure studies, are very worried about ultrafine particles because they sure look like they do a lot of damage in our body, but we don't fully understand the epidemiology yet. So, one of the things that we look at with our model is the ultrafine particle concentrations, and we can see again, a somewhat bigger effect for ultrafine particles than for PM 2.5 mass due to the adoption of these low carbon fuels. And so, it's something that merits further consideration from a scientific perspective. What does this all mean for the future? It's not just about PM 2.5 mass. It might be about other pollutants as well, like ultrafine particles. So I'll leave that out there as sort of a hint about things that we'll be thinking about at the university as we move forward. So with that, Colin, I'll turn it back to you, I think, for the final part of the presentation.
Sure. Thanks, Mike. And so, yeah, I'm going to go over a few sort of the implications and how we're interpreting some of these results. There's certainly a lot to go through here. After that, we are plan to go until 1 o'clock. So we'll start by taking the questions from the Q&A box. And then if there's any time left after that, we may try to see if we can unmute some of you and have a little more of a discussion, but we'll go for the Q&A box first. So certainly encourage you, if you have any questions, open to get those in there. So implication for the Clean Fuels Plan. And I definitely want to make sure that the headline isn't lost, because we are spending a lot of time about uncertainty in places where more work is needed and where we're going in. But it's pretty clear, and we have a high degree of confidence based on the results here, that the proposed expansion of the Clean Fuels Program is likely to result in significant health benefits due to reduced air pollutant emissions from vehicles. And so that's sort of the core finding, and we want to make sure we don't fall into the sort of academic habit of talking about the things we don't know more than we talk about the things we do. When we start digging a little deeper into this, this isn't a terribly surprising result. We would expect that you would have reductions in air pollution, because typically when you replace a petroleum fueled vehicle with any sort of non-petroleum fuel, there's almost always an air quality co-benefit. So this is not an unexpected result. And then the estimate of about 5 fewer deaths per million, and Mike discussed this a bit in his part of the talk, is based on modeling that covers the most heavily populated areas of the state. That's sort of like the western part of the state, and the health impact functions focus on people over age 30. So this quantitative analysis means that this quantitative analysis covers about 60% of the state population. So for the folks who are in the more rural parts of the state in the east, the expectation that is backed up by the modeling we did is that the pollution has sort of diluted to the point where it's kind of too small to really get a clean signal with the modeling and analysis tools that we have right now. And then, like Mike said, we know that younger people are definitely affected by pollution, but they're affected by different ways. And again, with the tools that we had for this study, we didn't dig deep into that, but there is ongoing work both at UC Davis as well as in Oregon and possibly elsewhere to get deeper into that. And one of the valuable products of this research study is we have the county level emissions from vehicles as well as the gridded air quality concentrations. So you can do a lot of this more granular, detailed public health analysis without having to go and do the really complex and computationally intensive steps of redoing the MOVES modeling and the air quality modeling. I know there are a lot of questions about equity and environmental justice. There is definitely ongoing work to sort of delve deeper into this particular topic. But we didn't have time to get as deep into it in this particular study as we wanted. But there are a number of things that we know and can infer. So we have seen that there's a clear air quality improvement around the major roadways and in major urban areas, and there's been a wealth of research in the environmental justice space that has indicated that disadvantaged communities, particularly lower income, elderly, disabled, people of color, are more likely to live near major roadways and more likely to be exposed to vehicle pollution, especially diesel pollution. And so given that we're seeing significant reductions near roadways, and there's historically the clean fuels programs tend to see changes in the diesel space kind of before the equivalent changes in the gasoline space, it stands to reason it's very likely that the Clean Fuels Program will help provide sort of a net equity enhancing effect. Now, again, these are inferences based on the quantification here as well as what we know. And we are currently doing work to get a more specific and granular and quantitative assessment of this. Mike discussed this as well in terms of valuing the health impacts. The net valuation based on value of statistical life, we just want to make clear that this isn't sort of taking the moral step of saying what a life is worth. This is a statistical measure of the total value of health impacts in situations where a population is exposed to pollution and sees some excess death. So essentially, we have tools that let us get that peak of that pyramid that Mike showed. We're estimating that peak of the pyramid, and the value of statistical life kind of infers the shape of the rest of the pyramid in a fairly approximate way. So certainly there are other ways to do a VSL measurement, and ongoing work is planned to better understand these health impacts and really to more specifically model the non-morbidity impacts, to really directly model the rest of that pyramid rather than trying to infer it from the size and the shape of the top piece. So I know there's some questions about scenario A versus scenario C, and I think that when you first look at it and sort of think about what they mean in terms of the clean fuel program, it seems a little strange that a scenario with a 37% target would produce, a very, very similar air quality result to the scenario with a 25% target. And that's, I think, in some ways an artifact of how these scenarios were developed in the initial sort of scenario development modeling, which happened, which ICF led and was done before we sort of became involved in this process. The main difference between scenario A and scenario C is that scenario C adds a lot of renewable diesel displacing conventional petroleum diesel. And like Mike mentioned in his talk, by 2035, pretty much all of the diesel fleet in Oregon is going to be made up of vehicles that are 2010 model year or later. And if they're 2010 model year later, they're going to have the diesel particulate filters as well as NOx control technology, most likely selective catalytic reduction, could be something else. These are sort of required by federal by federal standards. These emission control devices are very effective at reducing the particulate and NOx emissions from diesel engines. If they're operated well, they get well over 90% efficiency. And so even though renewable diesel does provide a small reduction in particulates and NOx from older diesel engines, the effect of these modern exhaust treatments basically knock the emissions of both of those pollutants down far enough that you can't really detect a statistically significant impact from renewable diesel in the new engines. So that's why it looks like this additional renewable diesel in 2035 just doesn't provide as much health impact as you might expect. Now, there's a couple things to remember with this. First, the renewable diesel is something that's being commercialized right now. Like I said, California already has about 25% of its diesel pool coming from diesel substitutes. And right now, in 2010, a significant fraction of the fleet is made up of these older diesel engines. So there are near-term emissions benefits that are not captured by our modeling because we focused on the sort of endpoint modeling under this proposed program. The other thing is scenario A was really looking at the deployment of ZEV. Scenario C added on this initial renewable diesel. In the real world, you wouldn't have sort of a one technology approach to complying with vehicle greenhouse gas regulations. It would be kind of spread more evenly over the fleet, and the higher CFP target would create a greater incentive and bring not just renewable diesel in, but other fuels as well. Also in 2035, there's a very good chance there's going to be fuels and technologies that are not commercialized now and are not captured in this modeling. So we think that the modeling, the effect of some of the assumptions we made and some of the assumptions at the scenario development stage mean that we might be slightly underestimating the net air quality impacts of scenario C relative to scenario A. But ultimately, what we think is clear is that the majority of the air quality benefit in 2035 is provided by the transition away from internal combustion engines and to zero emission vehicles. We also think it's very clear, or it's very important to keep in mind that even if there's not a massive particulate matter or other air quality benefit, the renewable diesel can still provide significant greenhouse gas reductions, and there are both environmental and health and economic benefits from the greenhouse gas impact. And so that's really it. So we can move on to Q&A. I've got the emails for both Mike and myself. Please feel free to reach out if you have any questions. If you have questions on the moves modeling or other elements, I'd say reach out to me and I'd be happy to connect you with the other members of the team. Like I said, we're going to start out by going through the the questions in the Q&A box, and I noticed that several of them have already been answered in writing. And then if we have time left after this, we can potentially go on to a bit more of a free-flowing discussion. So the first question we have in the Q&A box from an anonymous attendee: are we defining EVs solely as battery electrics, or does it include fuel cells? And they recommend we define EVs as both. For the purpose of this study, it doesn't really matter. Both of them have zero tailpipe emissions. So for the purpose of the modeling we did, there's really no difference. In the compliance scenario developed by ICF, it was almost entirely battery electrics. There was a small deployment of hydrogen, but certainly there's no reason why a final portfolio that tilts a little more heavily towards hydrogen would be impossible, and we don't think it would have a significant impact on the air quality impacts that we are talking about here. The next question from Bob Yunke is: did you consider the difference in life cycle emissions and of carbon and criteria pollutants associated with the different sources of diesel and soy, corn oil, food oils versus from non-food? So the differences from the different sources are captured in the greenhouse gas modeling that goes into judging compliance with the Clean Fuels program. So a renewable diesel made from a waste oil is going to have a much lower carbon intensity score and get a much higher amount of compliance credit under the program than one made from something like soybean oil or corn oil. From an emission standpoint, there's not a ton of difference. There are some emissions from the growing of soy and corn that might have an impact. Those were judged to be not likely to occur anywhere near the populated areas in Oregon, near enough to have a likely impact on the ultimate air quality. And modeling where biomass for energy or fuel crops is going to be grown is an intensely complicated exercise. I've spent a lot of time working on that myself. So we didn't, given where crops are grown and the industrial locations in Oregon, we didn't judge it likely that was going to cause a meaningful difference with the tools and the analysis we were doing. So no, we didn't, at least not from an air quality standpoint, but the program does consider that from a greenhouse gas standpoint. There's a question on how we calculated a more realistic VMT versus the MOVE's default. For this, we looked at VMT data from Oregon Department of Transportation and other Oregon stakeholders based on traffic measurements and in-state surveys. And so we sort of aligned the sort of starting point VMT expectations with Oregon's data more accurately, and then made sure that the long run VMT projections were at least in the same ballpark as the expectations that were done when ICF did the modeling for the compliance scenarios, just to make sure we were sort of modeling the same world. Again, if you'd like to get a little more deep into that, send me an email. I'd be happy to connect you with Guiwal Wong, who led the MOVE's modeling and can get a lot deeper into the weeds on that particular topic. Let's see, Mike, I see you're typing an answer to Cato Sanford's question. Do you want to go ahead and just answer it verbally, or do you want to stick with typing that one?
So you're on the answered window, I guess, right?
Yes, yeah. So if Cato Sanford, what types of vehicles were considered in the analysis? Was the fleet split according to gasoline, diesel, or there different weight classes? And if the latter, how do you account for the different? Yeah.
Right. So the emissions inventory that we get from the EPA, the National Emissions Inventory, does have different SCC numbers for different classes of vehicles within the broad grouping of diesel or gasoline. And so that is all in the underlying emissions inventory. When we get the MOVE's scaling factors by county, that also has a breakdown of different vehicle classes in the emissions inventory. And we are trying to line those two things up when we do the scaling to try to scale things appropriately, basically. Now, when we come to the air quality modeling, then when I tag things, I'm tagging everything sort of gasoline or diesel, but it's already been scaled sort of differentially by that point in time. And so it doesn't doesn't, I guess, smooth anything over excessively doing that, even though you can't see all of that complexity in the final air quality modeling results. I think it was handled sort of at a level of sophistication that's sort of commensurate with every other assumption that is in this project already. So it was accounted for, not perfectly, but I guess consistently is how I would say it.
Thank you. So we had another question from Cato. How do emissions from tire wear compare between heavy and light duty vehicles? Obviously, heavy duty vehicles, there's a lot more tire wear because they're heavier. There's more pressure. The MOVES model does include vehicle weight when it's considering tire and brake wear. We did not model any differences in tire and brake wear between EVs and conventional vehicles, or we would expect that you would have somewhat less brake wear from an EV because of the use of regenerative braking. There might be a bit more tire wear because EVs tend to be slightly heavier on the whole, but the emissions from those tend to be relatively small, and certainly smaller than the tailpipe emissions effects.
I guess one thing to emphasize then is we didn't change VMT between the 2035 business as usual scenario A and scenario C. So the tire and brake wear, was assumed to largely be consistent.
Yeah. Mike, this one's probably, you might be able to help. I'm not aware. Another question from Bob Yonke. Are you aware of any studies that estimate hotspot PM 2.5 exposure in schoolyards where buses idle and students are boarding, so you can look at specific health impacts? I know those studies are out there. I don't know where they are.
Yeah, there's lots of those types of studies in present day. And so in present day, you have many different options available for estimating exposure fields, not just chemical transport models. So you can have land use regression models, or land use regression models that are kind of married to Purple Air Network, married to satellite data. There's a lot of different ways to get 20-meter estimates for exposures. The problem is you don't have any of those tools available in the future. And so you basically have to rely on chemical transport models. We can drive chemical transport models to that high level of detail, but it's super expensive. And so it just becomes even more of a supercomputing exercise. So those types of studies can be done, but they just get progressively more and more expensive to do if you want to ask those types of questions in the future. You can try to use those other simpler techniques in the future as well, but now you're really extrapolating outside of area where you have data, which always is a concern. So if all the historical relationships hold up, then sure, you can estimate a child's exposure based on how close they stand to the bus stop. But if any part of the chemistry, the nonlinear chemistry changes in the future, meaning that those historical relationships don't hold anymore, then your estimate's going to be really wrong. So that's what makes it challenging for those types of studies in the future.
Okay, Floyd Vergara asked, does this modeling include benefits from the CFP expansion on fuels used in off-road vehicles and equipment? And I really should know this. I'm actually blanking on that. No, yeah, okay. So it doesn't. The scope of the study was on-road fuels only, and so we would expect there would be some additional benefits from off-road vehicles and equipment. A lot of those are going to be working in sort of rural areas, but yes, there would be some additional benefit. And certainly if those vehicles were not required to have the diesel particulate filters and SCR systems or other NOx control, then the renewable diesel would provide an additional incremental benefit there as well. Kathy Moyd was asking, do we take into account the expected changes from the climate protection program independent of those from the clean fuel scenario? No, we did not. It's modeling sort of the rest of the economy. It was just too complex and outside the scope of this particular project. Certainly that is a question of real interest, but we're really trying to look at what the air quality impacts of this particular program and this particular expected change are. It seems like based on health economic effects alone, there is no big advantage in accelerating the scrapping of older vehicles in favor of cleaner ones, including EVs. Is that a correct understanding of this result? Just let the stock turnover take its course. This is from Cato Sanford. I would actually say that's probably not true. I think, if there was a way to get a quicker turnover, particularly a turnover into zero emission vehicles, then you would just be, bringing the health impacts online much quicker. Certainly because, the diesel fleet in particular has kind of plateaued. You can reduce its greenhouse gas emissions, but you can't necessarily reduce its air pollutant emissions. So if there was an accelerated scrappage policy option available, that would improve the air quality impacts of a policy like this. It's just those are tricky to do in a cost-effective and equitable fashion. Okay. Question from Catherine Kolazar. Hi, Katie. Very nice study. What is driving the relatively larger decreases in EC compared to PM 2.5? Mike, this sounds like one for you.
Yeah, so the EC is a tailpipe emission, and so we're having a tailpipe effect here versus PM 2.5, which has contributions from wood burning, from food cooking, from lots of different other sources, and so we're seeing more decreases in EC because percent-wise, because that's a transportation source that's directly affected by this, whereas PM 2.5 mass has a lot of other non-transportation sources that aren't affected by scenarios that we're analyzing. And hi, Katie.
Fellow UC Davis alum that we both know. So next question from Floyd Vergara. Also, has any work been done to quantify the benefits between now and 2035 when there are presumably still significant numbers of pre-2010 engines from which the significant PM reductions can be achieved? Mike, this one sounds like for you, can you sort of linearly interpolate how valid would something like that be?
Well, we haven't done the work. I think that it all depends on the competition between the rate of clean fuel adoption versus the rate of fleet turnover to get the cleaner engines in there. If the rate of clean fuel adoption gets ahead of those clean engines, then sure, you can see some maybe enhanced benefits. But if the turnover sort of keeps up where the clean engines are sort of in the fleet at the same or greater rate than the fuels are, then I think that we largely wouldn't see any sort of nonlinear sort of temporary major increase in health benefits and then sort of a settling out. I assume that's what the interest is here, whether there could be some short-term sort of bigger health benefit than what we're analyzing here. And I think it just all depends on the rate of how quickly the fuels go in versus how quickly the engines turn over. We haven't done the analysis.
Yeah, I agree with all that. There's a question from Eric Feely. The effectiveness of the 2010 to 2023 engine pollution controls with SCR and DPF could vary with deterioration and especially tampering playing a larger role as the fleet ages. 2024 newer engines are likely to be an improvement due to the CARB NOx omnibus changes, and in 2027 with likely new federal standards means they'll be better controlled. How do you deal with the deterioration and tampering for model years from 2010 to 2023, since it can take a vehicle all the way back to an uncontrolled 1980s condition? That is a very good point. That's not something that we had the ability to really deal with here. I don't think there's particularly good data applicable to Oregon on what sort of the rate of tampering or poorly maintained emissions control systems are in the fleet. So that would be something that we would love to look at and we would love to consider, but it just was beyond the scope of this project, and I suspect kind of beyond the data we have available to make an informed answer. We have a question from someone else. Do you look at whether the use of carbon credits trading may affect the modeling or impact on air quality at all? So, carbon credit trading, first of all, Oregon doesn't have a cap and trade or sort of a traditional carbon market. There are carbon credits associated with the Clean Fuels program, but really all they are used to do is to determine sort of aggregate compliance at the state level. The air quality impact is determined by the way by the actual fuels that get deployed and the vehicles that are used, and that's what we looked at in this study. So it's I can't say it's absolutely impossible that somebody could come up with a creative way to game the Oregon system and get more petroleum into it. But as somebody who spends a lot of time working on these programs, that is extremely unlikely, and not something that we have really observed in practice in any of the low carbon fuel programs that have been around, for a decade in California and British Columbia, and for 5 years in Oregon. So the carbon credits, yeah. So our study looked at the kind of the end effect and what actually changes on the ground, and really all the carbon credits is a way to measure compliance at the statewide level. Next question, again from Cato Sanford. Having done the study, could you extract from your results some effective location-specific decay rates of the pollutants in order to bypass all the weather modeling? Meaning it would be faster to repeat the analysis next time. Mike, this one sounds like yours.
Yeah, so the weather modeling doesn't have to be redone, but I suspect what you actually mean is the chemical transport modeling in total. So certainly there are efforts underway in California to develop statistical models to try to, understand the relationship between emissions and health effects, or emissions and ambient concentrations in the future, using results like those that we produced in this project. I'm not leading any of those projects, and so I can't speak to the accuracy or success of those efforts. Coming from a more traditional background in air pollution, where we are very aware that the atmospheric system is nonlinear, and you can't just sort of assume that the changes to concentrations will be proportional to the changes in emissions. I think I'm hesitant to go down that path. So, but I think that there are a lot of researchers that are pursuing exactly that question. And I think that we can probably connect you with them in California if you're interested in looking at that in more detail.
Okay. So we have gone through all the questions in the Q&A window. I think there should be the ability for people to raise their hand. I think we should be able to unmute people who raise their hand if you wanted to ask a verbal question. Try and get onto the view. So
there were a lot of commentary in the chat as well. I'm not sure if any questions got embedded in there, but maybe during the verbal section, Colin, they can repeat them there, I guess.
Yeah, definitely. If there were, we tried to answer most of the questions that came through the chat window, and I think we did that. If we didn't get to your question in the chat window, then either raise your hand or re-enter it into the Q&A panel. But I'm not, okay, I see one raised hand. So, all right. Bob Yunke, you should be able to unmute yourself and talk now.
Yeah, I did raise the question about why you didn't include ozone, and particularly what I was aiming at was accounting for the impact of these hot weather events that we're now experiencing. And I know that those affect the ozone chemistry in the atmosphere. I'm not sure if they affect the secondary particle formation.
Yeah, that's a great question.
An important factor.
Yeah, so let's chat about that a little bit. And so there's been a lot of studies that show that when you have hotter temperatures, you tend to have more conducive ozone forming conditions. And so we would fully expect that ozone would increase in the future, due to the warmer temperatures. And so that is something that's a direct climate effect. It's not necessarily an effect of the adoption of low carbon fuels, or that we could move that number that much with low carbon fuels. In terms of airborne particles, everything that we've done so far has shown that you don't have a strong effect on the PM concentrations due to the warmer temperatures. There's too many compensating effects that are sort of driving, some of them drive the concentrations up, some drive them down. And we've done a lot of modeling in the West Coast in California. And statistically, there's just not a strong direct effect on the PM. So we focused on PM in this project, again, because that drives most of the health effect. But your point is well taken that the ozone probably.
Hey, Mike, I just lost audio for you.
Oh, sorry.
Oh, you're back now. Okay.
Okay. So your point is well taken, Bob. I was just saying that the ozone in the future probably will be higher due to the warming climate, and it probably does merit some investigation of how the ozone would change in these different scenarios. That wasn't really the focus of the current project, but it's a good follow-up question. We're pursuing a number of these follow-up questions as we sort of move this towards a peer-reviewed publication, and that can be one of them that we consider.
Great, thank you for the question. Are there any other questions? I see nothing in Q&A or chat, or are there any other people who would like to speak? If so, raise your hand. Okay, I see Katie wants to talk. All right, there we go. You should be able to unmute yourself.
Hi, sorry, I've got some noise in the background. Yeah, I know that you said that the off-road vehicles were not included, and as far as I understand, they're maybe not included in the clean fuels program, but how might those be accounted for? I know that the emissions are calculated using activity hours, so it's not really like a one-to-one with VMT, but is that something that would be important to consider, do you think, for how cleaner fuels for those which tend to have older diesel engines and aren't being phased out as quickly, what effect that might have?
Certainly they matter. Colin, I'll go first. So certainly they matter. They're in the emissions inventory. They're tagged with a unique source classification code in the National Emissions Inventory. So if we had some idea about the adoption of the cleaner fuels for those sources, it would be relatively simple to add those to the chemical transport part of the study. I think the harder part is getting a realistic estimate of what level of adoption would there be, and would there be competition, or would you be limited in the supply of those biofuels so that somehow now the off-road is competing with the on-road, and how's that going to work? And so I think all of the complexity comes sort of at the moves level, or the corresponding model for moves for the off-road sources, and any policy sort of decisions that have to be made about balancing out a fuel supply issue. So that's my take on it, but clearly outside the scope of this project, but could matter.
Yeah, that's basically what I would say too. The only other thing I'd add is a lot of times in clean fuel policies, people ask for exemptions for certain types of off-road vehicles, or often for lots of them, under the theory that they are economically important, particularly to protected communities. So it's a very good question, but it's definitely a non-trivial one to model.
Great, thank you both.
No problem. Mike, there was a question in the chat on sort of how many studies are underway to understand the ultrafine particulate impact. How extensively are they studied? Are they to be local, national, et cetera?
Yeah, so ultrafine particles, there's been some activity in California that I've been involved in, looking at sort of broad exposure areas and mortality. That was the California teacher study cohort, the 10,000 teachers across California. There have been ones that have been done with pregnancy outcomes, so preterm birth or low birth weight. And those kind of use the statewide birth registry. There are ones that are underway now for autism that are using populations in Southern California and Northern California separately. Kaiser Permanente is involved in some of this, so they're pretty big health systems. There have been ultrafine studies that have been done related to COVID outcomes that are underway. Sort of, do you have a sort of bigger chance of getting a more severe COVID outcome if you're exposed to ultrafine particles? So there's lots and lots of work that's sort of in progress. A lot of it's focused in California because it has a high population, and the emissions inventories and all the tools sort of started here, and they've got 30, 40, 50 years of sort of engineering expertise and development here. But I think that there's some national efforts as well. I haven't heard about as many of those and haven't been involved in as many of those. The hard part about ultrafine particles is that they're very localized. And so it's hard to put out a single monitor in the middle of a city and get an estimate for that whole city. You can kind of get away with that with PM 2.5, but for ultrafines, when you put out a single monitor, you know something about the 2 blocks around that monitor, and that's it. And so you need some way to estimate the broader population exposure. That's where our models come in. But again, this is a developing field, and most of the development has happened in California so far. We're excited to go other places, but we just haven't done it.
Sure. A couple more questions came in through the Q&A box. One was from Eric Feely on figure 1 of the briefing document that appears to show the most benefit from scenario A to be in Salem and north of Salem, Medford. Any thought about why Portland isn't showing as much benefit under scenario A?
I don't know off the top of my head, other than maybe just the comment that on a relative scale, how important is traffic in your community? It could be that in Portland, there are many other sources there that sort of make traffic not less important per vehicle mile traveled, but maybe there's, just in total, there's other things going on that sort of downweighted a little bit. You got a major airport there, you got other things in Portland that you don't have those other places. And so I suspect the answer kind of comes down to that, but we haven't analyzed it in detail yet.
Is there a prevailing wind issue? Is it possible that it's being, blown northeast, sort of away from Portland?
Well, I think most of the prevailing wind is from the west, right? Okay. And so I think that you're generally getting west or northwest sort of winds that are blowing things. So yeah, I guess certainly whether your freeway is to the west or east of your city matters as well in that whole game. That's probably an important fact as well.
Another question from Floyd Vergara. Even with modest reduction in co-pollutants in 2035, those reductions can have significant impacts at the neighborhood level. Have you looked at, or will you look at extrapolating these results to the EJ communities in Oregon and quantifying these benefits with a BendMap analysis? And then he also said, thanks us for the study and as well as to Oregon DEQ. So thank you for the kind words.
So that's a great question. We are doing that analysis at 4 kilometer resolution, which normally we would like to be at 1 kilometer resolution, but the work that we've done in California suggests that you can get information with just 4 kilometer resolution. So we're doing that here as well. We do have preliminary results on that, although we're not ready to really talk about them publicly. But maybe might want to mute Bob there.
There we go.
Yeah. So it is something of great interest to us. We are looking at it. I will say that the preliminary results that we have so far are a little bit different maybe than some of the traditional results that we've seen. And, in our analysis in California, what we've learned, I think, is that it's proximity to city centers that matters the most in the EJ analysis. No matter what we do, air pollution goes with people and the population density goes up as you go towards the urban core. So if you have a certain group that lives in that urban core, in almost any scenario that we look at, they're going to have higher air pollution compared to the people that live on the outer parts of the city. Now, Portland's a little bit interesting because Portland is pretty clean. And I think living in the urban core is kind of desirable. You have better access to transportation, public transportation, it's easier. And so the demographics of who lives in the urban cores in Oregon is a little bit different than the demographics of who lives in the urban cores in California. And so it's an interesting analysis where I know I put a few teasers out there. I don't want to go into more detail than that, but we are doing it. It's outside the scope of this project, though. I'd be clear about that. That was not within scope, but clearly we have a strong academic interest, and so we're pursuing it.
Sure. So we have another question in the Q&A from Ingrid Fish. So what is the main point or takeaway that you would like us as Portland policymakers and others to think about, and what actions would you suggest we take beyond the Clean Fuels program? First of all, obviously we're not from Oregon. We have no official position, and the University of California takes no official position about policy matters. But we do spend a lot of time thinking about climate policy and how to do this. I think you have to have a comprehensive portfolio. There is no single climate policy that can do everything that's needed in the time frame that's needed. And I do think that clean fuels programs are a critical part of that comprehensive portfolio. There's there's just, I think every jurisdiction, including Oregon, is kind of looking at a relatively similar landscape where because of the slow vehicle fleet turnover, you have to do something that reduces greenhouse gas emissions from conventional vehicles, and you have to consider those fuels on a life cycle basis. So that's really a CFP or an LCFS or something like that. They're very similar. I think at this point, at a broad level, electrifying everything as much as possible is a good idea. We know there's certain applications both in transportation and elsewhere that generally can't be electrified. We also know that there's going to be some challenges to electrify the grid, particularly to get the last 10-20% of the grid electrified to get to a very high renewable grid. Oregon is lucky that you have good hydropower resources, so that simplifies the grid transition a bit. But in general, I think Oregon's climate policy reflects the understanding pretty well. I think you just as much ambition as possible, and try to deploy EVs and clean up the grid at the same time, and do those as quickly as possible. And by the time we get to the parts that transition where there are still some open questions, the hard to electrify parts, that's a ways down the road. We have time to figure out what the solutions are and keep working on research to understand what the last step is. But there's a lot of steps that we can go, that we know what to do for the next 5 to 10 years at the very least. And generally speaking, Oregon's doing that. Okay. So once again, we are through all of the questions. I will take one last call for any raised hands or any additional questions in the Q&A box. Not seeing any. I just want to give one more sort of thank you to everyone who's involved. Oregon DEQ, Corianne Wind in particular, but also the rest of her staff, as well as the other Oregon staffers from Department of Transportation, Department of Public Health, and other offices who were very helpful, very collaborative, and generous with this process, and worked with us to try to get us as much data as possible and make this effort as reflective of real life as we possibly could. Want to recognize the ITS Davis team, Miriam McDonald, Sarah Schramer, and Christina Echeverry, who really helped set up the webinar and the website. I've said this in chat a few times. There's the website for this event will remain up, and it has links to the full report as well as the slides from today's presentation, and a single-page policy brief that's sort of written in plain language for a quick overview for non-experts. So please feel free to go there and avail yourself of those. And then, of course, I have to really thank the research team. This has been a really fun project to work on, as much as advanced computationally intensive air quality analysis can be fun. But I'm really happy with the amount of work we've done, and even though there were a number of challenges, I think we've definitely helped, and I think this study is likely to help a number of other states as they consider similar transitions. So thank you to Dr. Kleeman, as well as to Gui Hua, who I believe could not make today's seminar, and Yiting Li, who I think was on the seminar, who played critical roles in making all of this happen. So with that, I will end us a few minutes early, and feel free to reach out to any of us by our email on here, and we would be happy to answer further questions.
Thanks, Colin.
Thanks a lot. Have a good afternoon, everyone.